Greetings. Today we are looking at maximum work done in reversible expansion. So we want to look at the maximum work done in reversible expansion. So the isothermal expansion of an ideal gas can be carried out either through reversible process or it can be through irreversible process. So we can do this through these two options. Okay, so if we are to plot this, then we can have a plot pressure. Remember, we are talking about pressure volume work, so we can have that as our PV, so that we have V increasing in the direction and P increasing in that direction. Okay, so we start from a V1 here going to V2, and we can plot that from, if we move from point A to point B, there, from point A to point B, so that we have the volume changing those 2 points, and then pressure, we can have our P1 there, and then we have our P2 at that point. Okay, so if we look at this diagram here, this is a reversible work of expansion. When you expand, you can see the pressure reduces but the volume increases. Okay, so if you are then to determine the work done, then from P dV it will be equal to P dV, but we can be able to integrate from V1 to V2. So this is the reversible expansion, in which the pressure is falling from P1 but the volume is increasing. And so we can then generally express the work done irreversible to be equal to, remember these are negative, integral of V1 to V2 PdV. So that is what we have in this case. Okay, but we can also have a case where there's a sudden drop in pressure. Okay, so that we have pressure, volume, we move from V1 to V2, and then we're having our P1, there's a drop in pressure like that, A to B, somewhere there, so that we have our A aligning with V1 and B aligning with V2, and the pressure P1, and then we have our P2, sudden drop of pressure. Okay, so if you were to look at the irreversible work here, then we simply say that the work that is going to be done here when there's a pressure drop, sudden pressure drop to P2, we can express it. The first one we did was work irreversible. Okay, we have reversible, which is this PDV, but we're looking at work irreversible, which is now the minus of that, and we can simply indicate that if the expansion is performed irreversibly by the sudden reduction of pressure, okay, we reduce the external pressure to the final pressure P2, then W irreversible is equal to minus P into V2 minus V1, which is basically this area here. For this, we have our area, the whole of that. So you see the difference between these two. So in both processes, the state of the system has changed from A to B, but the work done is much less in the irreversible expansion than in the reversible expansion. Thus, mechanical work is not a state function, as it depends on the path by which the process is performed rather than on the initial and final state. So it is a path function. We also need to note that the work done in the irreversible expansion of a gas is maximum work that can be done by a system. And the system here is gas. So it can be done by a system which is gas in expansion between the same initial, which is A, and final, which is B. Okay, and we can be able to show that. So we have an example where we are told that 1 mole of an ideal gas at temperature of 25 degrees Celsius is allowed to expand reversibly at a constant temperature from a volume V1 of 10 liters to a volume V2 of 20 liters, and you're told to calculate the work done by the gas in joules or calories. And so we'll simply say that W is equal to minus nRT natural log of V2 over V1. And so if we fix the values that we have, we know that n is equal to 1. So we can also write this in terms of the normal log to base 10, which is, it comes to 2.303. Okay, times our R here will be 8.314. The temperature is 298, which is this plus 273, 298 log V2 over V1, and this gives us a value of minus 17.46 joules, and we can convert this to calories. Okay, so this leads us to the next thing that is called internal. energy, which can also be indicated as U. So what we are looking at here is that the total of all possible kinds of energy of a system is called the internal energy. And this is a sum of all possible energies that will be found within a system. Okay, so we represent it as U, or we can also represent it as E. Okay, so we can then determine change in internal energy to be equal to E final minus E initial. And delta E is positive if E final is greater than E initial, and it is negative if EF is less than E initial. So this is how we determine the internal energy. This leads us now to first law of thermodynamics. So in the first law of thermodynamics, it's an application of the broad principle of the first law of conservation of energy. Okay, and what it states is that the total energy of an isolated system remains constant, though it may change from one form to another. So when a system is changed from a state A to a state B, it undergoes a change in the internal energy from EA to EB, and thus we can write delta E to be equal to EB minus EA. So this energy change is brought about by the evolution or absorption of heat or by work being done. So we can determine it basically through the absorption of heat and or by the work done by the system. So because the total energy of the system must remain constant, we can write the mathematical statement of the first law as delta E is equal to Q minus W, where Q is the amount of heat supplied, while W is work done by the system. So you can get the full statement of the first law from the textbook. It can have various definitions and we can be able to determine that. So there are some special forms of the first law. Special forms. The special forms of first law of thermodynamics, and this comes from the statement that we have here of delta E is equal to Q minus W. So our first case, case 1, is for what we are calling cyclic process. In this cyclic process, and this is for an isothermal expansion of an ideal gas. In this case, the total change in energy, delta E, should be equal to 0. In a cyclic process, you start from point A, go through many steps, and come back to where you started from. So the overall change in energy becomes 0, and therefore, from our expression of delta E is equal to Q minus W, then it means that Q should be equal to W in a cyclic process. In the second case, case 2, we are looking at isochoric process. And isochoric here we are saying no change in volume. And so we note that here there's no expansion, no work of expansion. And so W is equal to 0, and therefore delta E will be equal to QV, because V is a constant. Case 3. Case 3 is for adiabatic process. Here, no change in heat. No change in heat, gained or lost. And so Q will be equal to 0. And so delta E will be equal to minus W. The last case, case 4, is isobaric process. Isobaric process, no change in pressure. And so from our delta E is equal to Q minus W, and we say that delta E will be equal to Q minus P delta V. We can have this because P remains constant. So we can have our expression that delta T is equal to Q minus P dV. So there are a number of examples that are given in your textbook that I would want you to look at, so that next time we look at enthalpy of a system. Enthalpy of a system, that is what we will look at next. Thank you.